You're back. Continuing the long journey here, we got another couple calculus questions. Not too bad. Let's get to it. So for 11, we've got a velocity formula and we want acceleration. Is the acceleration the rate of change of velocity, or is velocity the rate of change of acceleration? Acceleration is the rate of change of velocity, so we got to take a derivative to go for that. We just take the derivative. The constants go away because remember they're secretly multiplied by t to the 0, and so their coefficient would be 0. And so dt of v 4 plus 0.5 t squared, and that would just be equal to, the 4 goes away if you take the derivative, and then for this guy, our coefficient is just these two multiplied together, so it would be a 1, which we can ignore. I'll leave it there for now. And then our exponent goes down by 1. So 1 times t to the power of 1 is just t, so not so bad. And so if we want to know the instantaneous acceleration at 2 seconds, it's just 2. Not too bad. And then we got to do kind of the opposite. We want to find the displacement. Velocity is the rate of change of displacement. So if we want to go kind of backwards more towards the original function, we've got to use an integral. So we'll integrate our velocity function. With respect to t, and it would end up being 4t. If you want to know why, this is secretly times t to the 0. So we increase our exponent by 1, so it becomes t to the 1, which we don't write. And then our new coefficient is our old coefficient times the new exponent. So 4 times 1. Not too exciting. And then with this guy, we increase our exponent by 1, so t cubed, and then our new coefficient is our old coefficient times, or divided by our new exponent. So 0.5 divided by 3 is basically 1 over 6. And so if we want to find the displacement of the object between 0 and 6, we've got 4 times 6, which is 24, plus 1/6 times t cubed, so 6 times 6 times 6 divided by 6, which is just 6 times 6, so that would be 36. And so 24 plus 36, we got 60, and we are done. That sucker anyway. All right, we got this rock is dropped from the top of a 45-meter tower, and at the same time a ball is thrown from the top of the tower in a horizontal direction. Air resistance is negligible. The ball and the rock hit a level ground a distance 30 meters apart. We want to know the horizontal velocity of the ball. So basically, we want to take distance and divide it by time. Because the ball would have fallen straight down and the rock would have kept going, we've got to figure out the time. So we're going to use the height of the tower to figure out the time. They're both going to land at the same time because horizontal velocity doesn't affect how long something takes to fall. So I'm going to say d equals VIT plus 1/2 AT squared, but my initial vertical velocity was 0, so it's just 45 equals 1/2 times 10, because we're using 10 instead of 9.8 for these questions, t squared. If we then multiply both sides by 2 and divide both sides by 10, 45 times 2 is 90, divided by 10, we got 9, so 9 equals t squared, so t is just 3 seconds. It's a 9, yeah. And then it's just velocity equals distance over time. It got 30 meters away in 3 seconds, so it's just 10. Bam! All right, and then 14 is a little messed up. Lots of interesting, good distractors is basically the thing. In the absence of air friction, an object dropped near the surface of the Earth experiences a constant acceleration of about 9.8 meters per second squared. This means that the speed of the object increases 9.8 meters per second each second if it was dropped. If it was thrown up, it would be decreasing. The speed would be decreasing, but if it's dropped, it will be increasing. That is your answer. B implies you've got a constant velocity of 9.8 meters per second the whole time, which is incorrect. C implies the object falls 9.8 meters during each second, which again is the same as the B. D says the object falls 9.8 meters during the first second only. In the first second, it goes from, if you dropped it, it goes from 0 to 9.8 meters per second, with an average velocity of in between the two, which would be 4.9. So you actually only drop 4.9 meters in 1 second. So if you jump off the 5-meter diving board, or pretty much drop off it, it'll take you essentially 1 second to hit the water. And then the derivative of distance with respect to time for the object equals 9.8 meters per second. Derivative of distance with time is the rate of change of distance with time, which is velocity, not acceleration. So that's the problem. If it said the derivative of the velocity with respect to time for the object equals 9.8 meters per second squared, it would be right, but it doesn't say that. All right. All right, moving along, we got this car. It's got a mass, but it's in the kinematics section, so we can ignore it. It accelerates uniformly from rest, reaching a speed of 30 meters per second in 6 seconds. During the 6 seconds, the car has traveled the distance of. This is actually pretty easy. If it started at 0 and reached a speed of 30 meters per second and it accelerated uniformly, uniformly means you've got a constant acceleration. So if you want to find the average velocity, all you got to do is find the middle between 0 and 30, which is 15. So basically displacement equals average velocity times time, and your average velocity is just your middle between 30 and 0, which is 15, and your time is 6. So 15 times 6 is 90. So you went 90 meters. All right, 16, what do we got? We got stationary observer sees a package falling with speed v1 at an angle to the vertical. Cool. So you got somebody on the ground and they're seeing in a given instant. So in a particular instant, you can assume it's got a straight velocity. We're not talking about over a course of time because they wouldn't see it as a straight line at that point. So at a given instant, somebody on the ground sees this package drop from a plane moving at that speed. But from the pilot looking down, or hopefully somebody else in the plane looking down, it's good for pilots to pay attention, they would see it falling straight down. No, I'll still call it V-pilot because it makes a good name. And you want to know how fast is the pilot traveling relative to the ground? Well, now that I've drawn it this way, this is how fast the plane is going relative to the ground. The plane? I don't know. So this is the velocity. Someone sees the package going in a given instant as it's falling. This is, since the package has the same horizontal velocity as the person on the plane, in this whole like Newtonian relativity, they would see it as falling straight down. If you want to simulate this, start walking around and drop something. Someone sitting in a chair by you will see it going at an angle. You'll just see it fall straight down from your perspective. Anyway, setting it up like this, we got a nice right angled triangle and we just use Pythagoras. So it's, or what do we call it? I guess our V ground is V1 and our V pilot is V2. So anyway, if we want to find V plane, it would just be our hypotenuse, the square root of our V1 squared minus our V2 squared. And so there we are. So just Pythagoras. That one's a tricky one. It's kind of interpreting the question. And the actual logic's not terrible. All right, so we got an object launched vertically upward in the air with a positive initial velocity. Which of the following correctly describes the velocity and acceleration of the object at its maximum elevation? Well, at its maximum elevation, it'll slow down, stop. So its velocity is 0. Our acceleration is definitely, I'd go with negative. Yeah. I mean, it depends what you decide to assign it to, but yeah. Your acceleration is tied to force, and it's not like the force of gravity stops when something reaches its highest point. If it did, it would get to its highest point and then just hang there, which it doesn't do. So velocity goes to 0 at the highest point. Acceleration certainly does not. That stays constant. All right, this guy, we got this spring-loaded gun, fire a projectile to a height h if it's fired straight up. If the same gun is pointed at an angle of 45 degrees, what maximum height can now be reached by the projectile? So basically, we're changing what our vertical upward component is. So I'm going to do something, I'm going to do my let proof, my fancy proofs. So I'm going to say let h equals v over 2 times t. So average velocity times time. Well, that's not a great one because time will change. I will say instead, we'll do vf squared equals vi squared plus 2ad. We will rearrange. Final velocity is 0 at the highest point. And so I'm going to just make it v, whatever. V squared over 2a is equal to the height. Now, if we put something at 45 degrees, hopefully you've done special triangles in math, that means this thing here, if this is v over root 2. If you know your special triangles, 1, 1, root 2. Anyway, so basically, if you put in your calculator, like sine 45, you get 0.707, which is the same as 1 over root 2. Anyway, so h new, I don't know, our new height is equal to v over root 2 all squared all over 2a, which if we square the root 2, we get an extra 1/2. So figure out that if you square 1 over root 2, you get 1/2. And then aside from that, it's the same as it was before. So it'll be 1/2 the original height. So your new height, now that it's at an angle, is 1/2 the original. So that sucker. And there we are. And then if we keep going, we got velocity of projectile at launch is a horizontal component VH and a vertical component VV. Air resistance is negligible. When the projectile is at its highest point in its trajectory, which the following shows the vertical and horizontal components of its velocity, the vertical components of its acceleration. Your vertical velocity is going to go to 0, because again, it slows down, stops at the highest point. Your horizontal velocity is unaffected, but your acceleration is certainly still there, otherwise it would hang up in the air forever, which it does not. So your answer is E. And then this sucker, graph above shows velocity v as a function of time for an object moving in a straight line, which the following graph shows the corresponding displacement x as a function of time t for the same interval. So this is a graph of our slope. So we need our graph to follow this slope. So basically we got 3 chunks. We got a constantly increasing slope starting at 0. So we can almost solve it right here, because the only ones that start with 0 slope are D and B. So we've eliminated everything else but D and B so far, because it's got to start at 0 slope and then increase. So you got to tipping more and more up. And then our middle bit, we have a constant slope, a constant non-zero slope. The slope isn't changing, but it's not zero. So for our displacement graph, we need a constant non-zero slope. If it was zero, our slope would be right there, but it's not, so it's got to be d. And then just to show the last bit, you've got a constantly decreasing slope to zero. So notice, whoop, our slope goes to zero. And that's that guy. And then let's do the next two. So we can get this sucker done. So we've got a target T lying flat on the ground 3 meters from the side of the building that is 10 meters tall as shown above. Student rolls a ball off the horizontal roof of the building in the direction of the target. Air resistance is negligible. Horizontal speed, which the ball must leave the roof, it is straight the target, is most nearly. Basically, we would find the velocity by doing distance over time. Our distance is it went 3 meters. Our time we figure out from the height. So we'll do our whole d equals VIT, where VI vertically will be 0 because it's rolling off horizontally, plus 1/2 AT squared. Our d is 10 meters. Our acceleration, instead of 9.8, we're using 10. By the way, I'm making down positive in this case, because why have negatives if you don't need them? Cancel out our 10s, move the 2 to the other side by multiplying both sides by 2, and we got 2 equals t squared, or t equals root 2. And then it's just velocity is distance over time, which is 3. It went 3 meters in root 2 seconds as it fell. So this sucker. All right. This sucker, again, like one we did a couple previous, we're interested in our original graph, our like displacement graph, and we have the velocity graph. So we have a graph of the rate of change of our original graph. We have a graph of the slope of our original graph. And to start off with, we have a constant positive slope. So we need something that starts with a constant positive slope. The only contenders, this is 0 initial slope, this is 0 initial slope, this is, I don't know what the heck's going on there. So only E and A have initial positive constant slope. And then after that, the slope should go to 0, not the value to 0, the slope to 0, and then get negative, and then have a constantly negative slope. So this is just going crazy here. This is more what we're looking for. So we got initial constant positive slope, and then in the second section, the slope gets less and less until it hits 0. So that high point would correspond with that. And then it gets more and more negative, and then it becomes constant. Like that. And so our answer is A. That's it for now. We'll do the last 10 in the next video. Sorry for the length.